This video has been supported by JLC PCB. Hey guys, I once made a light-hearted joke at the expense of Germany's National Metrology Institute, the PTB. I should have known better, Germans being as humor intolerant as they are. Well, now it's retribution time. I got this menacingly looking email from them, suggesting that I should make amends by helping them dispose of a particularly big and heavy piece of scrap. I was supposed to come and pick that up in Paradise itself, located just outside of Brunswick in northern Germany. The Physikalisch-Technische Bundesanstalt is an interdisciplinary precision city. Unfortunately, I didn't get filming permissions inside, yet. But I did get something at least as nice. I adopted this old, broken Fluke 5700A multifunction calibrator myself. Who knows, maybe we can even bring it back to life. That would be a big deal. I'm told that this particular unit with parts from 1987 must be one of the earliest 5700s out there. Its series being launched officially in 1988. By now there are countless small hardware revisions and two major ones which have been released as separate products. First came the 5720A with some minutely improved specifications, but a nearly indistinguishable look. That has only just been superseded recently by the 5730A. What gets me all excited about the old chonker in front of me is that the analog fundamentals that all of these calibrators are based on have remained nearly unchanged over the last 30 years. So I like to think we are not that far away anymore from the top of the electrometrology food chain. I think the most important property of these machines is that they can be calibrated with only 3 external known references: 10 kiloohm, 10 volt, and 1 ohm. When given some alone time with these external standards, the calibrator will soak up some of their precision, only to redistribute it by generating whatever is needed to calibrate other devices. AC, DC, milliampere, kilovolt, and a wide range of resistances. Sound good? Let's see what we can do. This thing consists of more than 14 modules and hundreds of obsolete or special custom components. To make matters worse, Fluke's official product support lifecycle for the 5720, through which I could have gotten a few astronomically priced replacement parts, has just ended a few months ago. So as much as I would like to perform an initial smoke test, I think it'd be wise to fix as much as possible first. I'm not the first one with that idea, it seems. On this power supply filter board, somebody has decided to replace some of the aluminium electrolytic caps, as well as a small section of PCB material and traces. As a rule of thumb, I wouldn't recommend administering routine replacements to small patches of circuit boards. Even though this 1987 4-layer laminate, being bleeding-edge technology back then, isn't particularly good quality. It gets kind of soft at high temperatures, likes to delaminate and lose pads. So I'm going to remove the electrolytic caps as gently as possible, all of them this time, by dual-wielding soldering irons. Generally, whenever dealing with very valuable boards, I'm looking for ways to make desoldering safer. One great way to do that, whenever possible, is to dismantle components in situ, so that afterwards you can attack their remaining leads one by one. I like the story that patched hole in the board tells. It confirms my deep-rooted suspicions against carbon resistors. They drift like crazy, usually upwards, but they can still damage other components in their vicinities. So at least the carbon composition power resistors will have to leave as well. They may have a low inductance which gives them advantages when dissipating pulsed power. But ew, no such thing in my precision calibrator. Feels good, man. Although the entire calibrator is full of these suspicious parts, so it'll be a long and expensive journey. But hey, it'll be worth it 10 times over. I couldn't have let the thing operate over longer periods or even 24/7 with questionable components still cooking inside. The only way to do that worry-free is metal resistors and new high-temperature, long-life caps everywhere. Oh, and perfectly bent leads brought to you by the one and only Biegelehre, of course. Check out my authentic line of Biegelehre merch down below the video. Luckily, there's a service manual and schematics available for this product. For the Fluke, I mean, not for the Biegelehre. That way I know what goes where, and even more importantly, what it does there. Turns out this filter assembly has two more jobs in addition to rectification and filtering of the transformer voltages. It has an adjustable pre-regulator for the plus-minus high voltage lines, so that the precision stuff, when putting out 1 volt for example, doesn't have to drop the remaining 599 or whatever. And then there is also overcurrent protection. There is precise current regulation on the other side of the instrument, but I think it's good to have another safety layer here, in case something goes wrong on the way there. These are the off and low settings of the negative high voltage supply rail. They are working as expected. This is the high setting of the positive high voltage rail, which is on permanently for some reason. And this is the complete absence of overcurrent protection. I mean, sufficiently strong power supplies can sometimes vaporize their problems before vaporizing themselves, but I don't think it's the way it's meant to be in this case. I found that 2 transistors were to blame for these problems, who in their old ages had decided to become diodes instead. This SPS one in combination with a 5.1 ohm resistor is the current limiting one, and it happens to be a special selected high gain specimen for which I couldn't find a replacement part. I ended up just increasing the 5.1 ohm current shunt to 7. Gotta watch out for problems that may or may not cause down the line. But for now I got both the high voltage selection and the overcurrent protection working. I'm marking every new component with a white dot for when I have to recap this thing again in 30 or 40 years. It's not just a phase, Mum. I want to be a volt nut forever. That module supplies power only to the so-called guarded analog section. That's like the entire 75% portion on the left. The digital section consists of those 2 boards on the right and most of the front panel. No idea what kind of front penalty this thing has suffered, but it's not good. See those loose filament wires dangling around in there? Those are cathodes which emit electrons much more easily when they are heated to a few hundred degrees C. They grow longer when they are heated, so they have to be kept under tension. Just until they are heated too far and the filaments sproink. Obviously I'm not going to demonstrate that. These displays are way too awesome. Replacement parts with the correct pinouts are unavailable or very expensive, of course. I found one with the correct width at least, but it wants to talk USB, so not exactly a drop-in replacement. Let's see if we can find a culprit. The digital power supply, which is responsible for the vacuum fluorescent display, has these conveniently labeled test points like every other module in the instrument. 75 VUR, volt unregulated, is reading a happy 92 VDC. 75V, however, which is supposed to be the regulated version, is reading 4. Not really sure how to connect that to the busted display, but I like to imagine that the dead power transistor I found here just tried to do as much damage as possible on its way out. Replacing that actually gave me back my regulated 75 volt rail. And not sure if one can tell in the video, but that in turn gave me back both displays. The dot matrix one with multiple broken filaments is so dim it's hardly worth mentioning, but hey, better than nothing. It's a miracle that this is working at all and not just giving me magic smoke from the loose filaments making contact with the grids or the anodes. There is a bit more to do and to see in the front panel area. The keypad, for example, is working sporadically at best. To prevent the high voltage business on the display board from scaring the volatile ppms in the connector area, there is a lot of shielding in place, both behind and in front of the VFD. This is a somewhat transparent but conductively coated film. It's not exactly pretty, but its job is to be invisible, so that shouldn't matter. Same goes for yours truly. These are the low thermal EMF matched material connectors. Copper binding posts, washers, nuts, and cable lugs crimped onto silver-plated copper cable by the looks of it. I think that SMA connector is the only gold-plated thing in the entire instrument, or has been for the last 30 years. It is used only for the high bandwidth option, which I don't have yet. This is the over 30-year-old keyboard. Conductive silicone membrane keys are pressed onto these thick carbon footprints to short them out. This technology predates me and I've never met it anywhere else before. But as far as I can tell, now, the black tarnish on the carbon pads is what's preventing good operation. And a gentle, dry, brushy is probably the right method to restore them for another 30 years of service. What went through my head after doing this was something like, that's not clean enough. So I grabbed the IPA and started wiping away. Oops. I even tried to cover up this colossal screw-up by quickly painting them back on with conductive silver paint. But alas, my forgery left some to be desired. Luckily, this video's sponsor JLC PCB helped me out of this embarrassing situation quickly, and I think they even made my calibrator a little bit better in the process. I recreated the service manual schematics in KiCad. Then I took some caliper measurements of the original board to digitize that as well. Because this board is outside of multiple enclosure layers and only connected to digital circuitry anyway, I didn't want to copy Fluke's 4-layer stack-up with just large ground planes on the outer layers. I did, however, go for gold plating, which will hopefully make my keypads live a lot longer than that IPA-soluble carbon powder stuff. I should have suffered more for my mistake, but JLC PCB took the catharsis away from me by delivering this beautiful replacement part quickly and cheaply. A few friends actually expressed doubts about the suitability of electroless gold plating like this for membrane keypad purposes. The gold layer might just be too thin and wear off quickly, but I don't quite believe it. No doubt about it if we were talking about edge connectors like PCI, but these soft little rubber pads, I don't know. I guess I'll find out in a few months, and so will you. Because if I need another board, there'll be another sponsored video opportunity. There's another important feature on that board which I've just transplanted. It's one of, if not the best feeling rotary encoder I've ever laid hands on. And it's completely wear-free. They made that discreetly from ball bearing, laser-cut steel sheet metal, magnets and photoelectric fork sensors. Perfect for dialing in PPMs. That pretty much gives us a usable front panel, if the user has photomultiplier eyes or something. Oh well, I'll continue to try and find a suitable replacement display, but this machine is the most powerful when controlled remotely via GPIB anyway, so I'm not in a hurry. During booting it has already executed and passed this brief self-test, which involves mostly the digital circuitry. That's a nice start, but there is another built-in self-diagnostics program which is a bit more thorough. We are going to consult that when we are through with all the arcane analog modules, to see if any survive my interference. Let's fast forward through the final few mundane tasks to get to the good stuff quickly. I started to print some handles because the thing only came with 2. I pulled the CPU board out of the instrument and the notoriously forgetful EEPROMs out of that, being extra careful not to bend any leads. I dismantled the entire instrument front to rear to find even the last suspicious electrolytic cap or carbon composition resistor.
Enemy spotted.
I erased the handles and cured the EEPROMs in UV light. I took the disassembly even further. The 2 powerful fans and the absence of an air filter have accumulated quite a bit of dust in the chassis. That revealed even more of the marvels that were hidden in this beauty, like the potted and mu metal shielded mains filter and transformer, as well as the Bowden pulley mains switch and the fiber optical isolation of the analog part. I wonder what's in that mains filter.
Enemies.
Oh no, really? You've got to be joking. I gave the EEPROMs some new extra opaque labels. Then I reprogrammed and reinstalled them. The original fans sounded worn out, so they were replaced with some good quality similar airflow ones. Oh yeah, that's better. Oh yeah. There's something oily going on in the relay area over here. Not sure if somebody tried to use contact cleaner or if that's just leaking relay fluid. Either way, that's gotta go, just like every last little bit of dust. Selecting the right filter material is a bit of a balancing act. The higher the density, the more effective a filter can be. But if it gets too dense, it can impact airflow and ultimately the device's thermals. I went with this stuff for the time being. No idea if good, but probably better than nothing. And finally, while we are here, check out this rear connector situation, where one could connect a special Fluke power amplifier to source higher currents under the influence of the calibrator. They went with the thinnest wires possible for the sake of low capacitance. But gee, does that look frighteningly fragile. Hey, don't look at them too hard. Okay, I think that's a wrap. At least in terms of the easy stuff. Now we are going deep. I will continue to hunt down all the parts with a questionable reputation. Aluminium and tantalum electrolytic caps and carbon composition resistors. But the replacement process, pretty much the same as before, is not going to be the video's main focus anymore. Instead, in the following section I'd like to focus on what's going on where and why. Because, as I said in the beginning, the analog fundamentals are as relevant as always. This is A17, the regulator and guard crossing assembly. Can you guess which two main functions this thing has? This board is fed by the filter assembly, which we've already finished. It takes some of those rectified and filtered voltages and regulates them down to no less than 13 different DC voltage rails, to be used by other modules down the line. All low noise linear, of course, either buffered Zener diodes or integrated voltage regulators like 7805s. That's what it needs that huge air duct for, to keep everybody nice and comfortable. This module also contains the one and only in-guard processor. It is a special resident of the analog ivory tower, because it's the only one with the ability to talk to the digital mainboard and that way to the poisonous outside world. I want an in-guard processor of my own to make uncomfortable phone calls for me. Luckily, this guy only talks via duplex fiber link, so risk of noise contamination is fairly low. The in-guard processor controls all of the analog modules based on what the main processor commands. And so far it's been doing a great job. Applause. Next in line would be A16, the power amplifier. But for a coherent narrative, I'm going to mix up the order a little bit. So next up is going to be A11, the DAC, the heart and soul of this whole operation. Look at its shiny armor. One can tell right away that there's a big deal inside. Or it's compensating for something, like small men in big cars. Nope, that's legit alright. It has sub-cans after all, and two large hermetically sealed axial components. So the purpose of this digital to analog converter is to generate extremely precise and stable DC voltages between 0 and 22 volt. It does that like an Arduino would, with pulse width modulation. Sounds appalling, doesn't it? But with a few little tricks, it's actually fantastic in many ways. First, it needs the absolute best voltage reference possible. In this case, an ovenized SZA263 based module is used. The ultra-stable voltage that this thing generates becomes the high level of our PWM waveform. This, in other words. To generate arbitrary DC voltages lower than that, it only needs to adjust the duty cycle and low-pass filter the output. Digital electronics are very good at turning stuff on and off quickly. The Arduino comparison wasn't even that absurd. Such a super simple microcontroller, along with a standard issue crystal oscillator, can get you in the hundreds of picoseconds total jitter range, of which only a portion called deterministic jitter will have an impact on your filtered output voltage. Do the maths. A few picoseconds of uncertainty on top of millisecond pulse widths with which A11 is working equals spectacular DAC performance, that's all I know. There's also a special custom Fluke 22-bit ADC in here, which is a very important actor in the calibration of this calibrator. It's used as a null detector to compare and adjust itself to the previously mentioned 3 external standards. This precisely temperature-controlled hybrid module is the reference buffer, and the axial hermetic capacitors are a part of the PWM filter. Next in line is the Ohms main assembly, which is a lot more simple than it looks. It uses these 3 Fluke-branded hermetic resistor networks, which contain resistance values between 10 ohm and 9 megaohm, as well as an additional 90 megaohm fixed resistor made by Caddock. It synthesizes close approximations to the resistance values that the user has programmed using that battalion of relays, i.e. 10 ohm, 100 ohm, 1k ohm and so forth. What's nice about this topology is that it allows for 4-wire measurement on every value except for the 90 megaohm, where it doesn't matter anyway. The next one belongs to the resistance system as well, the Ohms Cal Assembly. This one adds a 1 ohm made from 4 4-ohm wire wounds in parallel, a 1.9 ohm made from 2 wire wounds, and a 0 ohm, which is probably just a PCB trace. It also has a battalion of these obsolete yellow relays for various configuration purposes, and a blatant isolated DC to DC converter right there in the middle. That seems a bit out of place in the middle of analog paradise, doesn't it? Well, I guess it exists for a good reason. It's part of a circuit that eliminates internal voltage drop whenever calibrating an ohm meter that can only do 2-wire measurement. Next up, a battalion of obsolete yellow relays for a change. I heard that all of these can start to fail quietly, lose a few ppms here and there, but nothing drastic enough to be noticed by the self-diagnostics program. Oh boy, that sounds like a good time, troubleshooting something like that. Because these relays are not available reliably anymore, I thought it made sense to pick some up cheap, just to be prepared for the inevitable. This is the switch matrix. It connects the output terminals to the various functions, or the various functions to one another, for self-testing and calibration purposes. There's also a times 130 gain amplifier on here, which seems to be missing one of these covers. It is used to detect and adjust 0 of most DC voltage ranges. Next we got a low current and high resolution oscillator assembly. Those 2 functions have nothing to do with each other. I guess they were just small enough to fit on the same board. Why do we need another current source anyway? Couldn't we just combine the voltage output DAC with the resistance synthesizer? Well, practically yeah, sure. But imagine your big shot industrial customers asking, how accurate is your current calibrator? And you having no better answer than a head-scratching, depends. Nah, this thing needs a proper transconductance amplifier that, within reasonable limits, doesn't care about the amp-meter impedance. It takes some extraordinary care to achieve this kind of performance in the exclusive realm of the nanoamps. Signal guarding, for example, and the entire transconductance amplifier, as well as the various current shunt resistors, are kept in another one of these precisely controlled hybrid ovens. I have yet to see something like that in a Keithley. The high-resolution oscillator on the other side of the board generates a variable frequency square wave, 10 Hz to 1.2 MHz, which is then reused, most importantly, by A13, the oscillator output assembly, where it's used as the AC output frequency. This module is based on a quadrature RC oscillator, with relay selectable feedback capacitors as sort of chores frequency ranges, and custom-made high-precision digital potentiometers as frequency fine adjustments within those ranges. These are the selectable film caps right next to the precision digipots in the shape of ceramic hybrid modules. This module is almost only concerned with the frequency of its output sine wave. It detects the zero crossings and uses a phase-locked loop to synchronize with the high-resolution square wave from the previous module. That's nice and all, don't get me wrong, But when calibrating a true RMS voltmeter, the amplitude is usually much more important than the frequency. Which is why there is an entire module dedicated to just that, the oscillator control board. Now, how do you even measure the root mean square value of an AC waveform with world-class metrology precision? It's defined as the equivalent DC value that would cause the same amount of heat in a resistor. Ordinary solutions are either discrete circuits that literally root, mean and square, while hoping that none of their components brings too much error to the table, or in more modern ICs, it's probably just a digitizer that hopes that nothing important happens in between samples. The Fluke way that is used on this assembly is a bit more direct than that. It's all based on these super special Fluke thermal RMS sensors, which also happen to be used in Fluke's 792A AC-DC thermal transfer standards, as well as their 5790A AC measurement standards. More details and teardown photos about all of these arcane devices can be found on xdevs.com. I'm just going to borrow this one so that I don't have to crack open my thermal RMS converter. These are basically just two matched pairs of resistor and transistor. One pair is heated by the signal to be measured, which influences its transistor current. The other pair is heated by an error amplifier, exactly to the point where there is no more temperature difference between the two. Well, and there we are already. The output of that error amplifier happens to be the equivalent DC value that causes the same amount of heat as the signal to be measured. Whew. Man, I sure hope these guys won't break before I have a working semiconductor, wire bonding and laser trimming setup. Hey, everybody seemed to like the longer videos, no complaining now. This is the power amplifier, which I didn't want to cover earlier, because we didn't know about any of its input signals yet. This module takes care of the voltage ranges that the DC DAC and the oscillator system can't deliver directly. 220 volt AC or DC, with some derating at the higher frequencies. For various reasons, this thing has been designed to be a 3-stage amplifier. The input stage is another one of those temperature-controlled hybrids for environmentally independent stability and low noise. The mid-stage adds most of the gain if needed. Its bandwidth is configured by relays, depending on what frequency range the calibrator is in. The output stage, including those heat-sunk power transistors, has no gain at all. It's just a follower, but with the highest current capability. Advantage being, that block is allowed to change temperature, because that doesn't add too much of an error. Semiconductors at elevated temperatures can actually degrade over time. So heavily heat-sunk power transistors are always worth checking. This patient has flatlined. Wow, we are nearly done. Second to the last is this innocently looking high voltage assembly, which is to blame, however, for a disproportionately large portion of worries. I didn't even see this myself. Tin from xdevs.com spotted this crack in the previously hermetic resistor network. Oh no, all the ppms are going to fall out. Well, the resistance values are still what they should be, according to the schematics. So I guess it's only the cover glass, and that appears to be bonded to the alumina ceramic substrate only by epoxy. That's a beginner hermetic seal in my opinion. Only real glass-to-metal seals count. Maybe I can borrow the ultrasonic soldering method from Applied Science and just put a big metallic snail trail all over that thing. But since that part is connected to such a big heatsink, I'd be a bit worried about thermal expansion coefficients of all the different materials involved in such a scenario. Oh well, that network is only involved in the 2.2 ampere current range anyway, so it could be worse. No clue what 2.2 ampere circuitry is doing on the high voltage assembly. And no clue either why they've placed the power transistors that are responsible for heating two of these hybrid ovens so closely together that they have created a hotspot. It almost looks like something broke here, but I can't find evidence for that. The heater resistances and the transistors are both fine. But I think I'm still going to replace the ones that have cooked the worst. With some special extra high power BJTs. I think most of the hybrid temperature controllers in here work the same. They are configured for either 50 or 62 degrees C so that ambient temperature never gets in their way. This one happens to be the high voltage divider for feedback purposes. The heater film resistor covers the entire ceramic substrate, so that there are no thermal gradients on it or on whatever is bonded to it. The temperature is sensed by a thermistor and the heater power is controlled proportionally by an op-amp. And the last one, finally. This one is the only module that needs screws to be undone before it can be pulled out. For good reason, it carries a heavy mu-metal shielded backpack. That is what actually generates the high voltage up to 1100 volt. A good old linear transformer, some rectifier diodes, and some relays to invert the polarity or to rewire the transformer windings for a different function altogether. What's ostentatiously missing though is the usual double half H-bridge, with which transformers are usually driven, as well as some kind of high voltage regulation. I would have expected an entire array of high voltage transistors, cascaded to withstand the full force of 1.1 kilovolt. Well, the 5700A elegantly reuses its existing modules. The oscillator system and the power amplifier work together to drive the transformer. The ultra-precise high-voltage control loop is closed by the ovenized 100:1 divider we've seen on the last module. That works both for DC and AC, just without the rectifier then. Here's the mind-blowing explanation for the presence of the 2.2 ampere range on the high-voltage assembly. All those relays can actually reconfigure the transformer windings to be either step up for high-voltage generation or step down for high-current generation. Absolutely brilliant. So anyway, how do you like the 3D printed handles? Wow, what a treasure chest this thing is. I think my lucky black gloves have touched everything now. And everything still seems to work somehow. In the next video we are going to have a special guest who will tell us how well we are really going to count those ppms. But generally speaking, what's next? What am I going to do with that beast? Well, I've got a number of multimeters here that haven't been calibrated in years or even decades in some cases. When they were last adjusted, ampere were still defined as newtons of force between two conductors. Got to bring them up to speed and tell them about cesium atoms and Kibble balances. The one multimeter that I've been lusting after for years still eludes me. So I would also like to use this calibrator to play around with ADCs myself and see if I can't DIY something better. Fluke's advertising material gives me the impression that a short warm-up time is sufficient for the 5700A. But it's obvious that this machine would love to be turned on 24/7 for maximum stability. To keep all those transistors biased and all those ovens at temperature, this unit draws 160 watt permanently. Some of that energy is transformed into noise or air movement in general. But I'm pretty sure that 95% of that energy is turned into heat, which was unpleasantly noticeable in the recent summer months. Unfortunately, German electricity is not that cheap, and I'm not sure if I'm willing to invest that much in ppms yet. At the moment we are freshly repaired and out of Cal anyway, so nothing really matters, and I have a bit more time to think about the energy side of things. Of course, I'm already looking hard for the holy trinity of external standards with which to perform the artifact calibration. I think I have 10 volt and 10 kilo ohm within reach already, but no clue how to find a world-class 1 ohm resistor. If anybody happens to find one of these guys, ideally 1 ohm or 10k, you know who to call. Reward to be negotiated. Here's a quick fast forward through that 10-minute self-diagnostics program, which uses the loudly audible relay matrix to connect hundreds of different test points, from all over the modules to the ADC. I was curious and captured a little bit of that with an oscilloscope in the middle of the repair. Didn't have its new fans yet at this point. What matters the most is that it doesn't find anything to complain about. I'm thrilled to report that at the end of this makeover, it didn't. Okay, that was a massively summarized version of this supermassive repair and rejuvenation project. The longest video I've made in years ended up being insultingly superficial somehow. No kidding, I could probably make a half-hour video just about the LT-Flu voltage references in this thing. Who knows, maybe I will. As soon as my dedicated YouTube voice has recovered. You don't have to wait for that though. The 570 pages worth of service manual for this series, countless lovingly handmade articles on xdevs.com, and the jungle of arcane knowledge that is the EEV Blog forum are out there, waiting. Knock yourselves out. Thanks for watching and see you soon.